Hello everybody, welcome to your lecture number 5 for historical geology. We're going to be going through some of the most basic igneous rocks, and starting off with this picture. One of my students joked looking at this beautiful school bus caught in Hawaiian basalt, and he kind of made a funny joke I always liked and said, this is Miss Frizzle's last ride. So that's the joke. But anyway, I do want to go through igneous rocks today, and Miss Frizzle, as usual, gets it wrong. You'll notice here it says this is actually an excerpt from the show, and it says Earth's so hot, the Earth's crust is melting. And I don't even know if you can see that because I'm kind of probably covering up, or it's probably like right here next to me. But if you can't read it, said Earth's crust, it's so hot it's melting. And actually, we're going to see later as we go through this lecture, that's really not true. The Earth doesn't melt usually because it's too hot. It usually melts because the pressure goes down. So we're going to see that you can melt rocks just as easily with decreases in pressure as you can with increases in temperature. In fact, that's much, much, much more common than it is to increase temperature to melt rocks. We'll see all that a little bit later as we progress through. So, we've talked about minerals, we've talked about the ionic bonds that hold minerals together. I hope you remember a little bit from our initial talk about minerals. We talked about a really important molecule, okay? So right on your lecture assignment, right, asks you, what's that most important rock-forming molecule that we encounter all the time in earth sciences and in geology and historical geology? And it's this one. It's your silicate molecule, okay? So most rocks that you see are going to be made out of silicates, okay? Silicate molecules. They look like that, all right? We sometimes call that the tetrahedron. So I'm going to kind of draw the shape that you would see here. And you can see it's kind of like maybe I should erase all the ink on the slide here. But if I drew it out for you, in fact, I'll get another let me get another color too, so it makes it a little bit more clear. If we draw it all out for you, you can see that there's actually kind of like a pyramid type shape that emerges here. It's not really a pyramid because, a true pyramid has 5 sides. This only has 4. So we call that the tetrahedron. Tetrahedron means 4-sided figure. Okay, so we call that the silicate tetrahedron. If I refer to in lecture or in talking more about rocks later in this class to tetrahedra, silicate tetrahedra, that's what I'm talking about. Okay, tetrahedron is one, plural tetrahedra. So that's what you want to draw basically for your next question on the lecture assignment, right? It wants you to draw out the silicate molecule, label the atoms in it, everything. So the interior atom there is a silicon, right? The outside atoms here are all oxygens. And what you're going to find is that these silicate tetrahedra love to link up, okay? They love to link up, and it actually creates different types of minerals depending on how those silicate tetrahedra link up. And more importantly, it's going to change the properties of the minerals. It's going to change the properties of the magma and the lava that is created. It's going to change everything. Silicate tetrahedra are incredibly important. How they link up, how they connect is incredibly important. Now take a look at this very important rock-forming mineral. I ask about what are the 6 important rock-forming minerals, okay? So one of the first ones, you have to write out the chemical formulas, right, for some of them. One of the first ones that we'll talk about here is olivine, okay? So remember that all rocks, we're talking about igneous rocks today, all rocks are made out of minerals. So this is one of the 6 most important minerals for rock-forming rocks on Earth. Here's the formula right there, okay? It's either iron or magnesium, okay? You can hopefully see that. That Fe is iron. It's either iron or magnesium, 2. You need 2 of them. And SiO4. SiO4 being a silicate tetrahedron. Okay. So I want you to take a look at the internal structure of olivine. We call this an isolated tetrahedron structure. So notice here that the tetrahedra are not touching. They're not linked up. Now I just want you to think about this for a minute. Is that going to make this mineral weaker or stronger? The fact that the tetrahedra are not linked up. If you're thinking weaker, that's correct. Olivine is very easy to destroy. It's very easily broken down chemically. It's also can be broken up relatively. It's a relatively, it's not so strong. I don't want to call it a weak mineral, but it's not as strong as many other silicate minerals. This is a mineral that's very easy to break down because of the fact that the tetrahedra don't link up. We call that an isolated tetrahedron structure. Okay. Now here's another very common of the 6 common rock-forming minerals, silicate minerals. Next one is pyroxene. So here's pyroxene. Here's the formula. I don't know if you want to write that one down. It definitely gets easier. There's easier formulas to write down, but if you want, you can write this one down. You could have iron, magnesium, or calcium, or some mix of those 3, Si2O6. Here you could see that the silicate tetrahedra are linked up in chains. We actually call these chain silicates. Okay, so the pyroxenes. The next are the double chain silicates called the amphiboles. The amphiboles. That's the 3rd that you should put down for 6 most common rock-forming minerals. Has a really crazy formula. I wouldn't advise you to memorize this or write this one down because it's pretty intense. Only if you're maybe a geology major do you want to know that one. But the double chain amphibole silicates, okay, these are, you can see 2 chains that are connected together of silicates. Now, as we get further and further along in terms of interconnectedness, you're going to find that these minerals get stronger and stronger and more difficult to chemically destroy and chemically break down. Next, we have the 2-dimensional or sheet silicates, the micas. And then finally, we get to the framework silicates, which are quartz and feldspar. So the final 2 that you can put for 6 most common rock-forming minerals are quartz and feldspar. Quartz has a formula of SiO2 for quartz. And for feldspar, we have a formula of either, well, it's actually written out right here, sodium or potassium, or some mix of the 2, that's in parentheses, aluminum, Si3O8. Maybe that's a relatively easier one compared to, amphibole is really crazy difficult, but maybe that's an easier one to write down for your assignment. So feldspar is actually the most common mineral of the crust, okay? And it's a really good mineral formula to know because you'll see that, you might remember from our lecture on Earth structure, that this contains really kind of like a mini version of the Earth's crust. Remember that Earth's crust, what were the common elements in Earth's crust? Oxygen, silicon, and aluminum, and then some iron. Now you can see that the 3 common things in feldspar are just those 3, oxygen, silicon, and aluminum. And in fact, it's in kind of the same proportions too. Remember, oxygen was first, then silicon, then aluminum in Earth's crust. And you can see that's the same thing here. 8 oxygens, 3 silicons, 1 aluminum. So it's actually like a little mini version of Earth's crust. So it's a good mineral formula to know. Feldspar is a really important mineral. It's the most common mineral of the crust. All right, now on to rocks. You know that rocks, what are rocks? They're just aggregates of minerals. They're just clumps of minerals, conglomerates of minerals that are all stuck together, glued together somehow. Okay, there are your 6 very common ones again: quartz, feldspar, mica, amphibole, pyroxene, and olivine, given to you in order of kind of most interconnected, where the silicate molecules are all touching each other, as in the case of quartz and feldspar. Okay, so these are most interconnected, to least, with that being olivine. Olivine is totally isolated, and that makes it the easiest one to destroy. All right, so a rock like granite, it's an igneous rock. It's a plutonic rock, we call it, and it's made up of basically 3 minerals: feldspar, quartz, mica. Sometimes there's some amphibole in there as well. So the black that you see in here is probably the mica, okay, the biotite mica. This gray color that you see, like right there and right there, a lot of that is the quartz. And then the white and the pink that you see that makes up most of the rock is actually the feldspar. So granite is by and large mostly feldspar. And guess what? You look at something like gabbro, that's probably a rock you probably haven't heard of before, mostly feldspar and now some pyroxene, okay? So rocks are made of minerals. Igneous rocks are no exception. And speaking of that, what are those three main rock types? Definitely you should know that for the test, right? You want to know what are your three main rock types. So those rock types are igneous, sedimentary, and metamorphic. We're focusing on igneous today. Okay. So let's take a look more closely at igneous rocks. So you know that igneous rocks, the definition of it, what defines an igneous rock? What defines it is it has to be formed from a melt. And maybe that melt cooled down or otherwise crystallized. By the way, there are more ways to crystallize a melt than just temperature changes. You can cool a melt down to crystallize it. That's the most common way. But you can also change the pressure to crystallize a melt. That's another common way that Earth cools its melts down and crystallizes its melts. Okay, so it can solidify in a number of ways. Pressure changes and temperature changes. So you have to be aware of that. Now, lava is that melted rock that's on the surface. So that's surface melt. But there's also other igneous rocks that form from the magma, and the magma is deep below. We have magma. So we call the kind of rocks that form from a magma, we call them plutonic rocks. So those are things like granite. Granite is an igneous rock, but it's called a plutonic rock. It forms underground, okay? And it forms from magma. Magma is melted rock that never reached the surface. Lava is the melted rock that did reach the surface. We call those kinds of rocks volcanic, okay? But both of them are igneous. So igneous can be split into either volcanic or plutonic. Okay. Now, if you just pick up a rock and you're looking at it, an igneous rock, how do you know if it's volcanic or plutonic? How do you know if it formed on the surface or if it formed deep below the surface? Well, we geologists, we actually have a way of doing that, and it's based off the texture. Now, the texture refers to something special when as geologists, we don't use the same word as other people. So I'm sure that when you think of texture, I would imagine probably most of you think of like, is it rough or is it smooth or how does it feel? That's what you think of maybe as the texture. Has nothing to do with that at all. I want you to banish that from your mind. That never has anything to do with what we're talking about in geology. Texture actually refers to the grain size distribution of the crystals in the rock. What does that mean? Well, if you look at these different igneous rocks, they have different crystal sizes, and they have different mixes of different crystal sizes. That is the texture. This, for example, we would call a coarse-grained rock, because all the crystals are large and you can see them. They're coarse, they're big. This, on the other hand, would be a fine-grained rock because you can't really see the individual crystals in there. Maybe this one would be kind of a mix. There are some crystals in there that you can see, other ones you can't. We actually call that mix porphyritic. Porphyritic. Okay, so you can have a coarse-grained texture. Another word for that is phaneritic. You could have a fine-grained texture. Another word for that is aphanitic. In Latin, or actually, I'm sorry, not in Latin, but in Greek, that word phan, that root word phan actually means visible. So aphanitic means, if you put an A in front of something in Greek, it means not, right? So not visible crystals. Two fine-grained crystals. Aphanic means fine-grained. Coarse-grained, phaneritic, means visible crystals, big visible crystals. That other term is porphyritic. That means there's a mix of some big, some small crystals, okay? And those are really important because the texture, the grain size distribution in the rock that we see is going to tell us where the rock formed. Did it form volcanically on the surface from a lava? Another word for that is extrusive. Or did it form inside the earth from a magma, plutonic rock? We would call that intrusive. Okay, intrusive. All right. So there you go. There's fine-grained, aphanitic, and coarse-grained, phaneritic. So we're going to look at that grain size, that texture, to determine if it formed from a lava or formed from a magma inside of the earth. This basalt is fine-grained, okay? It's fine-grained, it's aphanitic, and we're actually going to conclude that this therefore is volcanic. Another term we're going to apply to it as well as extrusive, okay? So basalt is fine-grained, it's aphanitic, it's also, that means therefore volcanic and extrusive. I think that you remember from our discussion of minerals that minerals are highly organized. I mean, look at these geometrical patterns that we saw, a lot of these examples, these very highly organized geometrical patterns in the mineral structure. All those mineral structures, that's part of what it means to be a mineral. You have a crystalline structure, you have a highly ordered structure. There's a place for every atom, there's an atom for every place. Well, if it's so highly organized, it's going to take time to build that structure. You know, think about your room, you know, it takes, or your house. What takes more time, to have everything put away in your room or in your house, or to just have everything scattered willy-nilly everywhere, just a big mess? Does it take more time to clean or take more time to make a mess? Well, it takes more time to clean. And the same thing is true with crystals or anything else for that matter. It's going to take time to put the atoms where they need to go to create these highly organized structures. So if you're going to have a big crystal, it's going to take time to make that big crystal. Therefore, coarse-grained rocks, like this granite, are going to take a long time to form. They need to have sometimes millions of years to make those big crystals. So these are going to form underneath the earth, where the cooling rates are very slow. Basalt and you know, lavas and things like that are going to cool very quickly, right? So if you imagine this lava flowing on the surface, it's going to cool really fast. It's going to cool really fast because it's exposed to the cold air. Whereas rocks that are forming deep underground are having time to cool, and therefore they're able to make this phaneritic texture. So we're going to look at the texture to figure out if the rock formed volcanically or if it formed plutonically. This is kind of a cool picture. This is, now, even though this isn't from Texas, I don't know if any of you have ever been to Enchanted Rock, but this could easily be Enchanted Rock, right? Enchanted Rock looks the same way. It's a big dome of pink granite, or domes of pink granite. They look just like this. These are actually old magma chambers that were brought to the surface through tectonic uplift and erosion, subsequent erosion. So what's really amazing is that you look at a big granite outcrop like this, you know, you can see it, I guess it's up here, and you're looking at this big granite outcrop, right? And this thing, just stand back and look at this in amazement for a minute, because this thing used to be, you know, 15 kilometers or 10 kilometers underneath the earth. And now it's at the surface. How did it get there? Well, erosion, uplift, tectonic uplift, and subsequent erosion removed the layers of rock that were on top of it and exposed it at the surface. So it's amazing that these things can form 10 kilometers underneath the ground but come to the surface eventually. Okay. So anyway, those are the main textural terms you should know: aphanitic, phaneritic. What's an example of a common plutonic rock? There's a lot of things you could put. Granite is one of them, but also gabbro, diorite. We're going to talk about those in a little bit. Okay, some other textural terms you might want to know. Porphyritic means that most crystals are microscopic, but there are some large crystals in it. So, for example, that's a porphyritic rock. You can see it's kind of a mix of fine grain and coarse grain. Vesicular means there's a lot of vesicles and bubbles. So that happens when you have a volcanic rock that had a lot of gas trapped inside of it. Almost looks like, I almost think of this, it looks like almost like rock bread, right? You know how like bread is filled with little holes and vesicles and cavities from like the yeast creating the CO2 bubbles and stuff. So same thing, you have these bubbles that are trapped in the magma, in the lava, and create this vesicular texture. A really famous one is obsidian, right? Obsidian has this beautiful glassy texture. This is like actual natural glass. It's glass that forms from volcanic rocks, from a lava. This is a pretty interesting video. I don't know if you'll be able to hear it. I'm going to turn the sound up all the way, and we'll see if we'll see if you can hear it.
When you hear the word lava, what do you think? You're probably thinking of a fast-moving red river of molten rock that's flowing down the side of a volcano like Etna. Most lava is like this, but there's a much rarer kind.
Okay, so I don't know if you can hear him or how well you can hear him, but he's just showing you, usually when you think of lava, you think of that like red river that's just flowing down. But this obsidian lava is really different. I want to take a look at the obsidian lava.
Lava flow, which is very seldom seen, but I was lucky to witness this at Cordon volcano in Chile, which erupted in 2011. This is an eruption that started with a real bang. It created a high ash plume that went all the way around the globe, but then this really thick, slow lava.
So this is the obsidian lava, and you can see it's much thicker and much slower than that normal like red river lava that you're used to seeing like from Hawaii. So it's interesting. Why is it so different? Again, it goes back to the silicate molecules. This obsidian lava has a lot of silicate in it, and the silicate is very interconnected. Well, if it wants to move and as a flow, as a liquid, it has to break silicate bonds in order to do that, and that's really hard. So because the silicate molecules are so interconnected, it really slows down the flow of this lava.
Oozed out for the months that followed. That's lava that it was still moving almost 1 year after the eruption stopped.
So again, I don't know if you can hear him, but he's saying this lava still, after eruption, is still moving 1 year later.
Obsidian lava is found all over the planet, but no one's ever seen one actually advancing before.
So anyway, I think you get the idea. Pyroclastic textures, kind of like a natural concrete, and these are formed when you have volcanic eruptions. So there's a really good there's a volcanic eruption of Mount Etna in Sicily, Italy, and you get these huge explosions. Now notice this is a lot different than the kind of eruptions that we get in Hawaii. And the reason is, again, silicate. These lavas have a lot more silicate in them, and it makes the silicate very, it makes the volcano very explosive, okay? And when you have more silicate, generally speaking, the eruption becomes more dangerous, more explosive, more deadly. Okay, so igneous rocks can have the same composition, but different textures, and then we'll give them a different name. So an example of this is basalt and gabbro. You could have basalt and gabbro. They have, if you took them to the chemist and had a chemical analysis, it would come back exactly the same. It's the exact same kind of composition. However, we give it a different name just because it has a different texture, and we know that therefore they must have formed differently inside of the earth. Gabbro has the coarse grain texture, right? That's the coarse. And this has the fine grain texture. Now on your test, you're actually going to have pictures like this, like you're seeing. And it's going to ask you which one formed volcanically, which one formed plutonically, right? So you kind of have to figure that kind of stuff out based off what? Based off the texture. Okay, so be ready for things like that. Coarse grain texture, so the coarse grained mafic rock, we call it gabbro. The fine grained mafic rock we call basalt. And I'm going to explain a little bit what I mean about that in just a minute. So before we go on, I just want to kind of talk a little bit about this. This will come up later when we talk a little bit more about plate tectonics. But how do you melt a rock in the earth? And one thing that is maybe hard for us to imagine when we're first starting off with geology is we tend to think of the melting temperature as one temperature, and that's not really true at all. In the Earth, melting temperature is actually a function of, depends on pressure. So what's the melting temperature of a rock? Well, it depends on the pressure. What's the melting temperature of any rock is going to depend on pressure. So melting temperature goes up as pressure goes up. So this is the melting line. It's a function of pressure. Melting temperature is a function of pressure. If you're on the hotter side of the line, you're molten. If you're on the colder side of the line, you're solid. So when you talk about melting a rock, it's a question of how do you cross the line? Well, I want to show you something here. There are a lot of ways to cross this line. You can go up. That's raising the temperature, and you melt the rock. But notice that you can also just go to the left. That's dropping the pressure, and you melt the rock. You might notice it's actually easier for this rock to melt by moving to the left than it is to go up, right? It has further to go by going up than it does going to the left. So dropping the pressure is going to melt that rock just as much as raising the temperature. It's really important for you to understand that you can melt a rock without any temperature change at all. No temp change. You can create a melt in an igneous rock. So you can increase the temperature, not common. Earth usually does not melt by increasing heat. Doesn't do that. You could have melting by low pressure. That is the most common way. 80% of all volcanoes on Earth form from low pressure. Pressure is lowered and it melts the rock. Okay. There's also the cheater's way. The cheater's way is you just move the line. You change the melting temperature. You lower the melting temperature. You can do that, for example, with rocks. You could do that easily by just adding water. Adding water to rocks will lower its melting temperature. It will depress the melting temperature, and it'll make the rock easier to melt. Okay. So let's talk about these different melt compositions. So I said we can actually categorize rocks, and we do categorize igneous rocks based on the texture, which we've already talked a lot about now, and the composition is the other half of it. So we have different ways we have different kind of terms, vocab terms, that apply to describe the composition of igneous rock. These are terms we only apply to igneous rocks. Okay, we don't apply these terms to sedimentary rocks. We don't apply these terms to metamorphic rocks. These are just igneous rock terms. Okay, what are they? The first term you should know is mafic. Okay, mafic. So a mafic rock, that term mafic, which I'm sure most of you have not heard of before, that mafic term actually means magnesium, and the fic means ferric, which is iron. It's Latin for iron. Okay, so this means that you are rich in, you can see, low silica content, and you're rich in magnesium and iron. Okay, so those are the elements that are elevated in a mafic composition. So it's low Si, low silicate, high magnesium, high iron. Now, on the flip side, we have the felsic rocks. Felsic rocks have high silicon content. They have no or low Mg, magnesium, and low iron. They also have high sodium and potassium. Okay. Now, you'll notice that there's actually a question about minerals that are common in mafic rocks and felsic rocks. Be really careful with this because a lot of students get minerals and elements of the periodic table confused. Magnesium and iron, sodium, potassium, silicon, those are all elements of the periodic table. Most of them are not minerals. And if they are minerals, they're definitely not minerals that are common or present in these kinds of rocks. The minerals that are common in these kinds of rocks are shown here. Mafic rocks have mostly pyroxene, feldspar, and olivine. Those are the main mineral constituents of a mafic rock. So a good example of a mafic rock is basalt or gabbro. Basalt or gabbro are mostly composed of pyroxene, feldspar, and maybe little bits of olivine. Felsic rocks, on the other hand, are going to have mostly feldspar and quartz. You'll notice that feldspar is in everything. That's why it's the most common rock of the crust, because it is in everything. It's everywhere. Probably when you pick up a random rock outside, almost certainly contains feldspar. Okay, now intermediate between the two end members, mafic and felsic, there's a aptly named composition called intermediate. Intermediate is extremely important. This is average composition of the continental crust. I'm going to put continental crust. Intermediate is the average composition of the continental crust. Okay, it is rich in feldspar and pyroxene, but also can contain like amphiboles, things like that. It's intermediate in its silicon concentration. These are very eruptive volcanoes, explosive volcanoes. They create high plumes of dust and ash when they go off. Mafic are the other end members. You know that mafic lavas are these Hawaiian-style lavas, and they have these very fluidic rivers of lava that flow. These are very low viscosity, low viscosity melts, and they're very fluidic, and they're very gentle eruptions. And that should make perfect sense because the silicate concentration is very low. When silicate concentration is low, the silicas don't touch each other. So they don't interconnect, and it allows the fluid to flow very easily. When silicate concentration is higher, like an intermediate or felsic, the silicates are all interconnected. That makes it a lot harder to break connections in order to flow. All right. So these are high in viscosity. They're also very explosive, and they're very dangerous compared to the mafic style eruptions. Okay. This is pie charts. These are pie charts showing you the composition of mafic, intermediate, and felsic in terms of elements of the periodic table. Okay. This is not the mineral content. Okay, so don't put this down for minerals. It's just showing you the elements of the periodic table concentrations in these. All right. Now let's go on to, you have a table to fill out, right, with your rock names for, and you should know all 6 of these, okay? These 6 of these rock names, these are very important rocks, okay? And you're filling it out based on the texture and the composition, right? Because that's how we classify igneous rocks, texture and composition. So mafic, coarse-grained rocks. Mafic rocks are basalt if it's fine-grained, gabbro if it's coarse-grained. For intermediate compositions, andesite if it's fine-grained, diorite if it's coarse-grained. And for felsic compositions, rhyolite if it's fine-grained, granite if it's coarse-grained. Pay special attention and make sure you know your intermediate rocks. These are extremely important. The intermediate rocks are the rocks of the continental crust. Average continental crust is made of andesite and diorite on average. Okay? Whereas mafic compositions are what make up the ocean crust. Okay, so I hope you remember that when we talked about the structure of the Earth. The ocean crust is mafic. Okay, the average rock type is basalt. Hope you remember from the Earth structure lecture, the average composition, the average rock type of the continental crust is diorite. Okay, things like that. Okay, so those are, and then we have igneous rocks that are just named off of texture alone. So, for example, a glassy textured rock is a glassy textured rock is obsidian. Pyroclastic rocks are called tuffs. vesicular rocks are called scoria, or if it's really vesicular to the point that it can float on water, we call it a pumice. Okay, so that's the different rocks named off of what do you call it? Off of texture. Okay, and this is a good slide, just kind of summarizing what minerals, right? What minerals are in the different compositions? Okay. What the silica content is of the different compositions, etc., etc. Okay, you do have a question from the reading as well. So make sure that you do that reading. It's important to keep up with. I know that the tests are mostly based off of the lectures, but it's important to get the same information coming from multiple different sources. So I do encourage you to do the reading. You have a whole chapter on igneous rocks, and there's some questions in there about ultramafic rocks, where you find ultramafic rocks in Earth. Okay. So do a little bit of reading on that. And it's actually important too, because some of the ultramafic rocks used to form on Earth's surface, no longer form there, but they used to form during in Earth's history. Okay, so anyway, do that reading, and besides that, hope you enjoyed the lecture. I'll catch you next time. Thanks for listening.